Gaussian distribution. Gaussian distribution is used to model continuous random variables. We had seen that Bernoulli distribution, binomial distribution, these were all used for discrete random variables. But coming to Gaussian, it is for continuous random variables. And secondly, Gaussian distribution is the most important distribution for a machine learning student because this is used for modeling most of the natural phenomena. Natural phenomena can be depicted using Gaussian distribution because of its special characteristics which we'll see. So this is the distribution of continuous random variables whose PDF, that is probability density function, forms a bell curve. What is a bell curve? It looks like a bell, that is this shape. The shape of a, let me draw it neatly, a shape of a bell. This is what a Gaussian distribution will always look like. And let us understand the parameters and various characteristics of a Gaussian. Let me draw the Gaussian on one side and from this we'll analyze. Okay. So if this is my graph, Gaussian will look something like this. That is, it will always form a bell curve of this kind. And the mean of the Gaussian, that is at the center of the distribution here. This will be the mean value. The first speciality is that the mean and mode of a Gaussian would always be the same. Why is it same? See, it is like this. What is mean? If you have, let us say, 1000 different experiments, out of the values that you obtained while you did the experiment 1000 times, if you take the average value, that average value is what you call as mean. It is also called as the expected value. And what is mode? When you did this experiment 1000 times, whichever value that occurred most number of times in the experiment, there would be some value. If you see, out of this 1000 times, let us say maybe 15 times or 20 times, which is the maximum number of times one particular value would have occurred. That value, that is what you call as mode. Coming to a Gaussian distribution, the mean and mode both are the same value. That is, see, this is the peak of the distribution. What does peak denote? Peak would say that this value occurred most number of times, right? And what is mean? Mean is the expected value. That is, out of all these values, if you average out, you will get this value. Coming to Gaussian, mean and mode are one and the same. The same value will be the mean as well as the mode. Coming to the parameters, what parameters denote a distribution? Coming to the parameters, first parameter is mean and second one is variance, which is denoted by sigma square. So if you know the mean and the variance of a Gaussian distribution, you will be able to identify any particular Gaussian distribution separately. So what is the significance of variance? Variance will tell you the spread or the dispersion of data around the mean. That is, if you know this is the mean and let us say your variance sigma square, then you can say that if you move this much away from the mean, the value would be this. So this is what variance tell you. What is the spread of data around the mean? If you move one variance, in general, in order to compare with the mean, you use standard deviation, which is sigma, that is the square root of variance. If you move one standard deviation towards the right from the mean, you will be able to say that this is the value at this point, or towards the left from the mean. See, towards the right and left, the value would be same in case of Gaussian. Same in the sense, the number of occurrences of that value would be same. Values will obviously be different because these are the values of x and this is your mean value. If you go towards the right, the value would increase. If you go towards the left, value would decrease. But the number of times this value would occur out of, let's say, some 1000 experiments, or in another sense, you can understand it as the probability of that particular value occurring. This would be the same if you move towards the right or left for the same distance. This is because this is a symmetric distribution, symmetric around the mean. Symmetric around the mean means from the mean, this is the mean value. if you move the same distance towards the right or same distance towards the left, then that value will occur the same number of times. Okay, number of times means actually it is probability, so I'm just mentioning as number of times. Let us understand the PDF first, the probability density function. I'm erasing this off. Coming to any distribution, you need to understand the probability density function because this will help you identify the distribution. So in the probability density function, we'll be using the parameters. One is mean, denoted by mu. The other one is variance, denoted by sigma square. Then what is our input value? Our input value is x, right? So from x, we should be able to find f of x. That is the value at that point x. So our f of x, this can be, so in the previous cases, Bernoulli or binomial, we were able to logically understand the formation of the probability density function. But coming to Gaussian, you won't be able to logically identify or understand the probability density function because it's not that simple. So it's better that you by heart this function for now, or automatically, if you are a machine learning student, as you move forward, you will automatically have this function by hearted because every here and then you will see a Gaussian distribution and you will have to do something with a Gaussian distribution. So as you see this 10-15 times, automatically it will be there fixed in your mind. So the probability density function of a Gaussian distribution, it is 1 by root of 2 pi sigma square into e raised to minus of x minus mu the whole square divided by 2 sigma square. This is the probability density function of a Gaussian distribution. So this is something that you need to have in your mind. 1 by root of 2 pi sigma square e raised to x minus mu the whole square divided by 2 sigma square. This is the probability density function of a Gaussian distribution. So if you put the values of mu, sigma square and x in this equation, you will be able to identify f of x, that is the value at that for that particular value of x. Let us understand different characteristics now. So once you identify these characteristics, it will be easier for you to understand why Gaussian is important and where is Gaussian actually used. That is, I told you this is used for various natural phenomenon. As soon as you see the characteristics, you will suddenly identify, oh right, so this is actually used in many places. Okay, so let us see the characteristics. So I'll draw the Gaussian here in the right side, and using this I'll explain each of the characteristics. Okay, so this is my bell curve, which is the Gaussian. Let this be the bell curve. So this is symmetric around the mean. From mean, this is my mean value. You move right or left, the left part and right part, it should look exactly the same. It should be identical. Okay, so this is the peak of the curve, which has the value mu, which is the mean. So the first speciality of a Gaussian distribution is that 68% of your total data would be in one standard deviation from the mean. So why am I using standard deviation instead of variance? Because variance sigma square is a squared term. So it's not easy to compare the value sigma square with your input value, which is x, right? Your mean, which is mu, this is comparable to the value of x, which is your input value. And sigma square is in squared terms of this x. So instead of sigma square, in order to identify the spread of data, you normally use standard deviation. What is standard deviation? It is sigma, which is square root of variance. So sigma is more in terms with x. So it is comparable with your input value as well as with your mean. So for this reason, we will be using standard deviation instead of variance in order to understand this logically. So the first speciality, as we discussed, is that 68% of your data would lie in one standard deviation from your mean. Let us understand this by taking an example. Let us say your Gaussian, this denotes the weight of all the human beings in the world. And let us say that the expected value or the mean is 60 kilograms. So I am taking this as 60 kilograms as the mean. So what does it mean when I say that 68% of the total data is within one standard deviation from the mean? That means if you move one standard deviation to the right and the left, you will be able to cover 68% of your total data. So let us say in this particular case, let us say standard deviation is 10, that is 10 kilograms, which means if I move one standard deviation from the mean towards the right, I'll reach 70 kilograms. If I move towards the left, I'll reach 50 kilograms. So within this range, that is, if you take from 60 kilogram to 70 kilograms, in this range, you should be able to find 68% of total human beings in the world. That is, see, these values are not actual values. I'm just assuming these values so that you understand the concept. Okay. So actually the average is not exactly 60, but I'm assuming that the average weight of a human being is 60. So in the range of 50 to 70 kilograms, you should be able to find 68% of all the human beings in the world if the mean is 60 and standard deviation is 10. So if you actually take the real world data of all weight of all the human beings, you identify the real mean and also you identify the real standard deviation. Using that, you should be able to depict it using a Gaussian distribution. Okay, so here we are just taking some example values so that you understand the concept. So this is the first characteristic, and the second speciality of a Gaussian distribution. Now we talked about one standard deviation. The second speciality is that if you take a Gaussian distribution, then 95% of your total data will be within two standard deviation from your mean. So considering the same example, if two standard deviation towards the left would mean 40 kilograms and towards the right would mean 80 kilograms. So according to this, if you take this range from 40 kilogram to 80 kilogram, you should be able to find 95% of all the human beings in the world are in the range of 40 to 80 kilograms of weight. And the third condition is that 99.7% of your complete data should be there within 3 standard deviation from the mean. So this means if you take 3 standard deviation, that is 30 kilogram to 90 kilogram, if you take this range, then 99.7% of all the human beings should be there in this range of 30 kilograms to 90 kilograms in their body weight. So this is how you understand a Gaussian. Take any Gaussian, it will always satisfy these three properties. That is, 68% of the data is within one standard deviation from mean, 95% of data is within two standard deviation from mean, and 99.7% of data is within 3 standard deviations from mean. So these are the characteristics or the specialities of a Gaussian distribution. The next thing is we have to understand the expectation and variance. So coming to any distribution, you need to understand, one is the probability density function, second thing is expectation, third thing is variance, and the fourth thing is the graphical representation. So coming to Gaussian, you already saw the probability density function. We already saw the graph. It looks like a bell curve. The next things are expectation and variance. So let us see how to identify expectation and variance of a Gaussian distribution. Coming to expectation of a Gaussian random variable x. So how do you normally calculate expectation? What is the formula for expectation of a continuous random variable? It is integral of minus infinity to infinity, that is over the all complete range of values. What do you want to do? You need to do x into f of x dx, right? This is how you find the expectation. So here f of x, in the sense the probability density function, that is what I meant by f of x here. So substituting the probability density function that we just learned, here you will get it as integral of minus infinity to infinity x into, what is your probability density function? It is 1 by root of 2 pi sigma square e raised to minus of x minus mu the whole square divided by 2 sigma square. So this is your probability density function into, okay, dx. So the integral from minus infinity to infinity x into 1 by root of 2 pi sigma square e raised to minus x minus mu the whole square by 2 sigma square dx. This is the this is what you have to solve in order to find the expectation. So in the previous case of binomial Bernoulli distributions and all, we had actually solved the whole thing. Here this is a bit complex, so we are not going to solve the whole thing because it will waste our time, and secondly it's not of much, no one is going to come and ask you to solve for the expectation. So this, if you solve, you're going to get mu. So this is your takeaway from this, that is the expectation of a Gaussian random variable is mu, which is the mean value, right? So we had this is quite logical, this final understanding that we got, that is if you have a bell curve like this, you know that mu is the mean, so expected value should be this only, because this is the most probable value. If you pick one value randomly from this particular Gaussian distribution, most probably you will get a value at this point, the peak mean, right? So because most of the values fall in that point, so the expectation of a Gaussian random variable is mu, which is the mean. Next thing is variance. Let us see variance. Variance of a Gaussian random variable. What is the variance? The formula for variance is expectation of x square minus expectation of x the whole square. This is what we had already seen. And we know expectation of x, this is mu, and expectation of x square. So again, expectation of x square, I am again not going to solve. Instead, I'm just going to tell you what is the final value, because we just need these values here in order to calculate variance. That's the whole thing. So expectation of x square, if you put this formula as integral of x square into f of x dx, if you do that, you will finally reach mu square plus sigma square. So this is your expectation of x square. Substituting this here, you will get mu square plus sigma square minus, what is expectation of x? It is mu. Expectation of x square would be mu square, right? So if you do this, you will get as sigma square. You got it as sigma square, which means your expectation of a Gaussian random variable is mu, and variance of a Gaussian random variable is sigma square. So this is the takeaway. So in this lecture, we had seen about Gaussian distribution. We saw the probability density function of a Gaussian distribution. Then we saw the specialities, why this Gaussian distribution is special and why this can be used for depicting all the natural phenomena. Then we also saw the expectation of a random variable, of the Gaussian random variable, variance of the Gaussian random variable. We also learned about the graph structure, how to draw the graph of a Gaussian distribution.